Okay, welcome to a video on factoring using greatest common factor and also special products or special cases of difference of squares. I have two examples for you. This first one, 4x to the fourth minus 4x squared. The first thing I always do is I look at the terms and see is there a common factor to both terms. Well, 4 is common to both terms, and x squared can be divided into both terms. So I'll separate out 4x squared. If I divide the first term by 4x squared, I end up with an x squared left. And the second term, if I divide 4x squared by 4x squared, I end up with a 1. Now, when I divided the 4x to the fourth by 4x squared, you're just subtracting the two exponents. The exponent 4 minus the exponent of 2 leaves you with x squared. Okay, now I have a special case, x squared minus 1. So that I can further separate as x minus 1 times x plus 1. Because this is a difference of squares, x times x and 1 times 1. Okay, I carry down the greatest common factor, and that's my final solution for that expression. I've factored it down as far as I can. Now, if I want to verify that this is correct, I can go in reverse. I'll use the FOIL method, and I'll multiply these two expressions, binomial expressions. I'll end up with first x times x, outer x times 1, inner minus 1 times x, last minus 1 times plus 1, which is minus 1. Now these two, plus x and minus x, will cancel each other out and give us a 0. So we're left with just x squared minus 1. And we still have that greatest common factor. We bring that down, 4x squared. If we multiply that using the distributive property times each term, we end up with 4x squared times x squared. When you multiply two exponents, you're just adding them. So you end up with 4x to the fourth. And 4x squared times minus 1, which is just minus 4x squared. So, lo and behold, this is the same as the expression we start out with. So yes, this method does work. Okay, we have one more example for you. And on this second one, we have 12a squared minus 15a to the fourth. And again, the first thing I always do is I look for the greatest common factor. So in these two terms, I have an a squared that's divisible into each term, and I have a 3 that's divisible into 12, and a 3 that's divisible into 15. So I'll take out 3a squared. That's my greatest common factor. So if I divide 12a squared by 3a squared, I'm left with just 4. And if I divide 15a to the fourth by 3a squared, well, you subtract the exponents when you're dividing. So 4 minus 2 gives me a squared. 15 divided by 3 is a 5. And a to the fourth divided by a squared leaves me with a squared. So that's my expression. And this is not a difference of squares because I have a 5 is not something that has a something times itself to give us 5. So really this is as far as we can take this one. And if we want to double check that, we can just use the distributive property. This is the solution. But if we use the distributive property, we see that 3a squared times 4 is 12a squared, and 3a squared times 5a squared gives us 15a to the fourth. And that's the expression we started with. So here are two examples using greatest common factor, and in this case difference of squares. In this case we couldn't do that.